Hi, everyone. So I want to introduce myself. I'm the undergraduate student from the Michigan, and previously I transferred from the U of I, and I work with the Daniel Cooney. And this project is my sophomore year product because after moving to the Michigan, I'm more focusing on the computational neuroscience, doing some network theory and infectious disease. And also moving to the Michigan, I work with Naoki. So really happy to see some of my undergraduate research manager here. And then, so I will move to the Princeton in this fall, become the applied math PhD student. And today's I want to talk about something is about the spatial pattern formations and evolution of cooperative behavior. This title comes from the Daniel's talk from the GMM because it's really hard for me to think about like really concrete, maybe the titles for this. Okay. Next things I want to talk about. So organizing this talk, I want to divide it into the four parts. So basically, we want to talk about something is that we want to talk about the hawks and the doves will move in the space, and they can have the different rules. So, and I organized this talk by my two papers with Dan Cooney. The first one is my first sophomore summer work, talk about the spatial pattern formations and with the evolutionary game theory. And the second paper is the ML project. It's actually like the 1 semester long project. And we continue doing when moving to the Michigan. And there is also the co-author training transfer from the U of I goes to the Caltech. And so for this talk, we will talk about the four different motion. The first is that so if the species just diffuse purely random motions in the space, and the second we want to talk about if they would like to based on the different rules moving in the space, we can the hawk and doves we are chasing the better payoff, and then we will incorporate some non-local payoff driven motion. And the last things we want to talk about is the environmental driven motion. The individuals will move goes to the better environment. And the next things I want to talk about is the tragedy of commons to talk about some backgrounds. Because I remember I used to make some cartoons in the sign dynamical system in the Denver previous year. Because I love to tell some stories about this. And yesterday, because when I come to this workshop, I listened to a lot of talk about the evolutionary game theory and AI. So these stories will also tell about how the evolution of AI. So firstly, I want to talk about is overfishing. Overfishing is exactly the good maybe the examples about the tragedy of commons because we were extraction of the common resources. And then the interesting cartoon for this I made by the AI last year will look like this. So if we have the two fisheries, one is for me and one is for them, and if we want to maybe we are selfish because we want to catch more fish. And then you would find that we will be unhappy at last finally because if we want to catch as much as fish we can, and you will find there are no fish because we know if the fish want to grow from the zero to the current capacity, it will take a lot of time because if we catch all of the fish, there will be no fish. And then, but I think this would be the happy ending because yesterday I used the AIs to make some other figures because that's original figure I present in the last conference. So, but after like there are no fish in the ocean, we realize we were from the same group in the future because I will work with Dan's advisor in the Princeton. And so I remember last year I come to the Princeton to visit Simon's lab, and Simon gave me a mug, and the mug will say it's a Laven's Lab Common Resources. So these things inspire me. We are from the Princeton, and we got we are exactly extract the Laven's lab resources. So we think we need to cooperate. And then, so we from the higher, the higher efforts harvesters become the lower efforts harvesters. And then we reduce to fishing at first. And you will find the fish populations will grow up. And then we always like to fish populations at its peaks. And we will not to fish a lot. So later on you will find maybe we can get our better payoff for our boats. So this is what I'm want to talking today. And so Firstly, okay, I want to talk about our setting. So we have the Hawk-Dove games. And so we write down the payoff matrix and use the V and C's in terms of the Hawks and the Doves payoffs. And we know the P is a punishment and R is a reward. And T is a temptation and S is the sucker. And right now is a V minus C over 2 form. It's just the Hawk-Dove games. And this is our basic settings. And then we want to write down things is about the write down the payoff. The payoff for the pH will equal to the P times the U over V, this is the fractions of the cooperators. And the V will be the fraction of the defectors, the fractions of the defectors is the Hogs. And then we want to write down the long spatial models with the variable population size because now we assume the total populations is not a constant. So we will assume the per capita rate of each of the population will proportional to their payoff. This would say if they can get a higher payoff, they can reproduce more, they can have more offsprings. And then we write down the constant death rate for the two population by their sum. This would say their constant death rate will regulate by the logistical growth. And then this is the non-spatial models because we assume the individuals will diffuse in the space so they can do the random walk. And then we write down the purely diffusion motion, and we can derive this from the Markov chain. And they just have the pure diffusion term for the du and the dv. And the du dv would be the diffusion coefficient. And then we have like some similar recipes to derive what's the condition for the spatial pattern formation, because spatial pattern formation will correspond to the stable for the if we just consider the ODE the time dependent, and it's unstable if we consider the spatial movement, and then we derive the spatial pattern formation condition. This would set if the du is much greater than the dv, this would be the Hogs will move much faster than the Doves, and we would get the spatial pattern. And next question is that how the spatial pattern looks like, and we can do the numerical plotting, and we assume the dv is equal to the 0.1, and the du would be the diffusivity of the Hogs, and you would find it's almost about the 50 times than the dv, and we can plot the long time behavior, and you would find about the cosine patterns because we assume so it will have some L would be the total length of the landscapes, and it will show the cosine pattern. And the next question for this paper is that because in the 1 semester long programs for the research, and we have the two groups. So one for the PDE, I did almost all the parts about the PDE, and the collaborators doing something about the stochastic parts, they will assume they use the GLSP code to say the individuals can move around the space, and they do the similar settings, and they set up the mu v for it's the diffusivity, the movement rate of the Doves, and the mu u is the movement rate of the Hogs, and they use a similar ratio, and they find across the space they will also show like some cosine function patterns you would find. So it will show something like the cosine function patterns, and then you would find there are some different points between the PDE and the stochastic, because you would find here because of the boundary condition. Here, the boundary would have like some points is really high and really low, because near the boundary, if you go to the boundary, they cannot go to the out of the boundary, so they can just go back. So this would be the problem of the stochastic parts. They always have some points near the boundary will show like the higher amplitude, the larger amplitude. And the next question we want to ask is that whether this pattern is good or bad. And so we just assume the dv is equal to the 0.1. We fix the dv, and we vary the du. It's the diffusivity of the Hogs, and because this would be the critical du would be just if we just above the critical du, and we would to observe the patterns. And we find if we increase the diffusivity of the Hogs, the total populations will become higher, and also the average payoffs will also become higher. So this would say if we just do the random walk in the space, the pure diffusions will will help them because they can achieve the better payoff across the space. And then we also want to average the things in the stochastic part, and we find basically they agree with each other because you would find above the critical mu u, the patterns will appear, and all of the individuals and also the payoffs will go higher. But there is a point for the payoffs. The payoffs will be the flip because for this one you would find the higher payoff would be the doves, but for this the higher payoff will achieved by the hogs. So this would be the difference between the stochastic part and the PDE. And next thing we want to ask is that we want to derive the model for the payoff-driven motion. For the payoff-driven motion, basically we derive these models is from the chemotaxis model because we want to assume the individuals we are chasing the better payoff, we are chasing the gradients of the payoff, and they were based on some different payoff rules. And the rules we typically choosing here is that we choosing the functions just take the exponential. They will take the exponential form, and the WU, WV will be the sensitivity parameters for the payoff-driven motions. If they have the higher U or higher V, this would say the individuals will be more sensitive to the higher payoff, and then they would move faster. And what we do for these models is that we do the linear stability analysis. And we find there are no finite wave number patterns because in the PDEs, if you want to chasing the individuals, you will have a really fast self-aggregation. So we would find there are some no finite wave number patterns. So, but we think about these problems is because of the PDE. So we want to do using the stochastic parts to do the similar things and to see what the pattern looks like. And we do the stochastic part, we assume the mu u is equal to the mu v. And then we also find there exists some kind of like some cosine function patterns. It's like some wave patterns. And then we also want to understanding if we want to address this problem in the PDEs, how could we like to fix this problem? So we consider the non-local payoff-driven motions. This would be the individuals will no longer chasing the higher payoff, and they will chasing the region. They have the higher payoff, and we assume the radius of the region will become the rho, and this would become the average of the higher payoff, the payoffs in that region. And we assume and we simplify these models can also do the linear stability analysis. And we find in this model the finite wave number patterns exist. So we use the non-local payoff-driven motions to fix the problems in the payoff-driven motion because they cannot see the pattern. And then we also want to ask the questions is about if we can have the better environments, because in the better environment, you would think the individual can get the higher payoff. So this would be some of the similarities as a payoff-driven motion, because the individual chasing the better payoff, whether this would be equivalent to the individual we are chasing the better environment. Because in the good environment, they get a higher payoff, and in the bad environment, they got the worst payoff. And then we propose the models is about the eco-evolutionary games. And so we assume the payoff matrix. Here we use L and H. The L will become the low effort harvesters, and the H will become the high effort harvester. You could think about the LH is like maybe the cooperators and the defector, because the low effort harvester will say you would like to consume the resources just a little bit, not a lot, and the high level harvesters will be says you would like to want to maybe like to catch as much as a fish they can. And so we write down the linear eco-evolutionary games, and we write down the payoffs, and we coupled with the n. N would be the environmental metric. When the n is equal to the 1, these linear payoffs will become the R1, S1, T1, P1, and when the n becomes 0, this payoff matrix will become the R0, S0, T0, and P0. And I want to also talk about this is because we read this paper because when I was a sophomore undergraduate student, I take the differential equation taught by the them, and during that time, I doing some readings. And the Tillman, Josh, and Arrow paper, these papers would be the first paper I read in the 21st century. Because originally, I read some of the papers in the last century about the Simons papers and about like some other like some spatial movement papers. But this one is the first paper I raised in the 21st century. So during that time, I said, could we doing some models based on this and in this summer? So this is the first like the inspirations of this project. And so in these models, we carefully follow this model, and we assume there are like some renewable resources. We will assume the renewable resources would grow as the logistical growth. And then the second term, the AMELP plus that second term will set the cooperators and the defectors want to extract the resources, and then they have the different efforts, EL and the EH. And based on these resources stocks, and we do the linear, they do the linear change of the variables, do the mappings, and this would become the environmental matrix dN over dt. And we'll write down as this simple form. And here P would be the fractions the fractions of the L type individuals, and the 1 minus P will become the fractions of the H types individuals. And then we also write down the payoff matrix, and we do some assumptions. Assumptions, we rank in the payoffs. The R0 greater than the S0. This would mean if I'm the cooperators, I facing the cooperators and the defectors, and I would more like to facing the cooperators. And the T0 greater than the P0 would do the same things, and it's also similar to the R1 and the R1, S1, T1, and the P1. And we also assume the R1 greater than the R0. All of the corresponding terms, the R1 is always greater than the R0. This is because in a good environment, they can go to the higher payoff. So we encode these mechanisms into this like some setting of the payoffs. And then we can write down the payoffs we average by the lower efforts and the higher efforts harvesters. This is just the efforts for each of the payoff matrix and linearized by the n. And we assume the U would be the number of the L type harvester, and the V would become the number of the H type harvester. And then we find, according to the Tillman's papers, we find the cycling behaviors in the eco-evolutionary games would have they would exist the long-time oscillations is possible. So this would say they would have the Nimi cycle behavior. And this would also to say this would be the oscillating strategy of the comments. And in my previous examples about me and then we have the fishery to extract the fish, and then later on we said, oh, we want to protect the environment, we want to get more fish. This would be the case of the oscillating strategy of the comments. But this would not be the good ending, because good ending is I think we are from the same lab, so we cooperate in the future. But this would say if they become a good environment, they will harvesting, and then the environment become bad, so this would have the naming cycle behavior. And then we want to write down the non-spatial models. This would really similar to the previous one, because we assume the per capita birth rate is proportional to the payoffs, and then we have the constant death rates. We're regulated by the sum of their total populations, and we have the dn equations. And here this epsilon will provide the relative timescales for the individual updating their strategies relevant to the strength of the environmental feedback. We have these parameters, and then we want to write down the full spatial models for environmental driven motion. Here we assume the individuals will still do a random walk, but then they will chasing the better environments by chasing the gradients of the environmental metrics. And we also assume there are the function Fn would be the some rules of they move across the space, and here we assume the Fn will become the e to the n. So these terms will exactly become the u and partial over partial x n. So this would say is the individual we are chasing the gradient of the better environment. And so we run on these models, and we also want to follow the same recipe to do the linear stability analysis to see whether this pattern is good or bad. Because in our previous PDE parts in the payoff driven motion, there are the infinite wave number patterns. And here we do the similar procedures, and we assume the du is equal to the dv, and we exactly derive the formulas for the chi-u. This chi-u would say is the spatial pattern formation occur when the chi-u is much greater than the chi-v. This would say is the cooperators will move much faster than the defectors and in the space, and we can see the patterns. And we want to also plot the long-term behavior, long-term outcomes achieved by these models, and we assume and we find the minimum Chi-U star is equal to this number, and we just to set up the Chi-U is just a little bit above that, so this can confirm they have the unique wave number patterns. And we do these things, and we find the uniform state is a 0.4. You would find the average payoff across the space is lower than the equilibrium states. This would introduce a spatial dilemma because everyone wants to chasing the higher payoff. In some of the region, they can reach the higher payoff, but other regions will become really worse. And we will also to calculate the average population across the space for the U, V, and N, and we find that the average U will become the lower, and the average V, the number of the hogs, will become higher, and the total environment will become worse. This would say if we want to be the selfish, we want to extract the common resources more, the total environment will become worse in the space, across the space. And we also want to know the impact of the environmental sensitivity. So we increase the sensitivity of the environmental motion of the Chi-U, and we find if the U move faster, much faster, and the environment will become worse, the average environment, and also the average payoffs will become worse. And so there are like the main takeaways. We know the twin type spatial patterns merge when the hawk move faster than the doves under the pure diffusion motion. And we find the higher hawk mobilities increase both population size and average payoffs in both stochastic and the PDE models. This would say the purely diffusions is good in the settings. And we know the random movement promotes the coexistence and spatial patterning that's benefited the entire populations. And we also know the directed motions by the sustainable harvester towards the improving environment. This would say if the individual want to chasing the higher environment, the total environment will become worse. And although they can produce the regions, they have the higher payoff and the higher environments, but for the whole environment and the whole average payoffs will become worse. And then I want to advertise some about the Python package. This is write down by the collaborator training. He did a lot about the stochastic part, and we write down he write down the package for here, and they can do the simulations using the Python, and just to download the package, and you can do all the simulations about stochastic parts in the paper. And finally, I want to say some recommendation ratings. The first one, I really appreciate this paper. This paper would be on the first 21st century paper I read in the academia. And the second paper I want to advertise is because Cooney's lab become larger and larger. And so they have like some following projects about the spatial public goods. This would say the individuals will produce some signals, and the individuals will chasing the better that signals. And so this project is yesterday in the poster sessions, and they present this part. And also the third papers when I do this project, Cooney dances a lot because this is, he said, is one of the Daniel Cooney's favorite papers, and the other one must be the Shishilo. And the fourth papers, this is about the chemotaxis model, because for these two papers we really carefully modeling as a chemotaxis type, and a lot of things about the chemotaxis models in this paper. And finally, I want to thanks for the UFI, and they give me some monies for my living during the sophomore year summer. And also thanks to the Dan for his guidance, because originally I thought I will take a PhD in the quantum physics, but after doing some readings with him, I changed by him. So this is like, I really thanks to him. He introduced me to the evolutionary game theory and the mathematical biology. And later on, even though I doing more research on the math bio, like the computational neuroscience, I decided I want to switch back to do some evolutionary game theory in the future. So thanks for all the attending and the listening. Thanks.
Sashi. Yeah, thanks for the nice talk. I have a question about the pattern formation thing. And you showed that if hawk diffuses faster than the dove, then the pattern appears. And is it relevant to Turing instability? Because you said that the Turing-like thing happens, but according to the Turing instability, if the Hawk is an inhibitor of a dove, then the Turing pattern appears. That's what the Turing, predicted. But I don't see that the Hawk suppressing dove or something. So is it really Turing instability?
Oh, I think it's true instability, and originally because of the notion, I think it's the hawks move much faster than doves, and they would have the true instability.
Yeah, but
Oh, you mean in the ODE part?
I mean how hawk and dove interact matters to see whether it's a real Turing instability or the Turing instability like thing happening.
So I think it's the true instability like things happening because we do the linear stability analysis is just based on the the stabilities for the ODEs and the instability for the PDEs, and we find the something like the spatial pattern happens. I think, and also we can assume like some different regions for the hawks and the doves, like because humans is the hawk inhibitations, and so I think we're doing these things both, and in the papers, and we find it's all can produce the two instabilities, the spatial pattern formations. I think.
Thank you.
Yes, and here we just choosing the one examples for that.